In this video, we will be covering related rates, specifically an example that revolves around the concept of a circular equation. Now, recall related rates is nothing more than a concept that there is a function and the rates of each variable in that function in some way are related to each other. So, we're going to look at this example here, where if the radius of an oil slick is growing at a rate of 3 meters per hour, then how fast is the area of the oil slick growing when the radius is 12 meters? Notice right here, this is the equation that we're going to be given. So, for this first equation, I have A equals pi r squared. This is the relationship of the area of any circle to its radius. Now, if I know that the oil slick is growing at a rate of 3 meters per hour, that means that if I have a circular region here, and let's just say this is the oil slick, this is the radius value here, and every hour the radius is going to change from what it was to 3 meters more than what it was. So this would be our radius plus 3, and the time on that case would be 1 hour later. Now, with this information understood, I can take a look at this equation, and I can say, well, if I take the derivative of the area in respect to time, then I can take the derivative of this side of the equation in respect to time as well. So d dt of this side of the equation. Now recall, pi is just a constant, so the derivative of a constant times any function, that pi, that constant, can be carried out of that derivative. So now it's just d dt of r squared. Now the derivative of any function squared, remember, is 2 times that function, r, to the power of 2 minus 1, which is 1. And then I have to make sure I keep in mind what is the derivative of that variable inside the function. So what's the derivative of r in respect to t? And that's where we write dr dt. So again, the derivative of r squared is 2r. The derivative of r, the inside function, is dr dt. I will then carry down my pi value, and this is all equal to dA dt. So, I've taken the derivative of the original function. Again, this function is not always going to be provided. Sometimes you're just going to have to be able to draw the picture, identify the equation that relates the information that we're given, and then we're going to go ahead and have to take the derivative of that function. After taking the derivative of that function, let's identify all the pieces of information that we have. First off, the radius of the oil slick, meaning dr dt, is growing at a rate of 3 meters per hour. So I'm going to go ahead and put 3 meters and then per hour. Notice again, this is dr dt because it's the rate at which the radius is changing, or growing in this case. One of the detail about this that's important is that it is growing, meaning that this is going to be a positive rate. If this was shrinking at that rate, then we would have a negative sign there. Then the question is how fast is the area of the oil slick growing? So I want dA dt. What is dA dt equal to when the radius is 12 meters? So now I have all this information here. I'm looking for a dA dt, which I do have. I have r, which I have in my formula, and I have dr dt, which I have in my formula. So simply by plugging all of this information in, 2 times 12 times 3, this will provide me with the value that I'm looking for. In other words, I'm going to have, looks like 72 pi. And then what's the unit of measurement on this? Well, this is dA dt. Let's talk about what A is. A should have an area measure, or meters squared. Again, a single length, r, would have a meters area, which is squared length, so that's going to be meters squared. If this was a volume, it'd be meters cubed. And then since it's dA dt, it's the change in the area, it's the change in meters squared over the change in the time unit, and the time unit in this case is hours, because that was given in the beginning of the problem. That right there is the final answer of what we're looking for in this problem.